Have you ever stopped to think about what your hand is actually capable of? Right now, without looking, you could pick up a coin from a table. You could button a shirt, write your name, play a musical instrument, or feel the texture of a piece of fabric with astonishing precision. All of these actions seem effortless, yet behind every movement lies one of the most sophisticated structures ever produced by evolution: the human hand. A biological machine capable of generating tremendous strength and extraordinary precision. A structure so versatile that even the most advanced robots still struggle to replicate its abilities. And perhaps, most remarkably, a structure that acts as a direct extension of the human brain. Today, we are going to explore the anatomy, mechanics, and neuroscience of the human hand. From bones and tendons to nerves and sensory receptors. From powerful grips to delicate movements measured in fractions of a millimeter. And by the end, you may never look at your own hands the same way again. The story begins beneath the skin. At first glance, the hand appears relatively simple, but inside lies an intricate framework of 27 bones. More than a quarter of all the bones in the entire human body are located in the two hands alone. 8 small carpal bones form the wrist. 5 metacarpal bones create the framework of the palm, and 14 phalanges form the fingers and thumb. Together, these bones create a structure that is both remarkably strong and extraordinarily flexible. But bones alone cannot produce movement. That responsibility belongs to a sophisticated network of muscles and tendons. Interestingly, many of the muscles that move the fingers are not located inside the hand itself. They are located in the forearm. When these muscles contract, long tendons transmit the force into the hand and fingers. This arrangement allows the hand to remain relatively lightweight while still generating substantial power. Additional muscles located within the hand provide the fine control necessary for delicate movements. These small intrinsic muscles allow us to manipulate objects with extraordinary accuracy. They help us type on keyboards, thread needles, paint detailed artwork, and perform countless tasks that require precision. Yet perhaps the most important feature of the human hand is the thumb. The opposable thumb is one of the defining characteristics of our species. Unlike most animals, humans can bring the thumb into direct contact with the tips of the other fingers. This simple ability dramatically increases the number of possible grips and movements. The thumb alone accounts for a significant portion of the hand's overall function. Without it, many everyday tasks would become surprisingly difficult. Writing, using tools, opening containers, operating machinery. Even holding a cup would become a challenge. The importance of the thumb becomes even clearer when we examine how humans grasp objects. Scientists generally describe several major categories of grip. The power grip is used when maximum force is required. For example, when holding a hammer or carrying a heavy suitcase. In this grip, the fingers wrap around the object, while the thumb locks it securely in place. Then there is the precision grip. This is the grip used when picking up a small screw, holding a pen, or performing surgery. In these situations, tiny adjustments in finger position become critically important. The ability to transition seamlessly between power and precision is one of the hand's most remarkable capabilities. But movement is only part of the story. The hand is also an extraordinary sensory organ. The skin of the fingertips contains one of the highest concentrations of sensory receptors found anywhere in the body. These receptors continuously gather information about pressure, vibration, texture, temperature, and movement. Every time you touch an object, enormous amounts of data flow toward the brain. Specialized receptors respond to different kinds of stimulation. Some detect light touch, others detect deep pressure. Some are sensitive to vibration. Others respond to stretching of the skin. Together, they create an incredibly detailed map of the external world. In fact, your fingertips can detect surface features measured in fractions of a millimeter. This sensitivity allows you to distinguish materials, identify objects without looking, and manipulate fragile items with astonishing control. None of this would be possible without the nervous system. Three major nerves provide most of the hand's sensory and motor functions: the median nerve, the ulnar nerve, and the radial nerve. Each carries signals between the hand and the brain. Among these, the median nerve is particularly important. It travels through a narrow passageway in the wrist known as the carpal tunnel. This tunnel is formed by bones and connective tissue. Under normal conditions, the nerve passes through freely. But when pressure increases within the tunnel, the nerve can become compressed. This condition is known as carpal tunnel syndrome. Millions of people worldwide experience symptoms such as numbness, tingling, weakness, and pain as a result. The condition highlights how dependent hand function is on healthy neural communication. Every movement of the hand begins as electrical activity inside the brain. Regions of the motor cortex generate signals that travel down the spinal cord and into peripheral nerves. These signals activate muscles with remarkable precision. At the same time, sensory information travels back to the brain. The process is continuous. The brain sends commands. The hand provides feedback. The brain adjusts. The hand responds. This constant loop allows movements to remain smooth, accurate, and adaptive. In fact, a surprisingly large portion of the human brain is dedicated to controlling and monitoring the hands. Neuroscientists often illustrate this using a representation known as the cortical homunculus. In this map, the hands occupy an enormous amount of brain territory compared to many other body parts. The reason is simple. The hand performs an extraordinary variety of tasks. To support that complexity, the brain must devote significant resources to controlling it. The relationship between the hand and the brain has helped shape human history. Hands allowed our ancestors to create tools, build shelters, produce art, develop technology, and eventually construct entire civilizations. The evolution of the hand transformed the evolution of the mind. Even today, despite tremendous advances in robotics and artificial intelligence, engineers continue to struggle with challenges that the human hand solves effortlessly. Robotic hands can be powerful, they can be fast, some can even be highly precise. But combining strength, flexibility, adaptability, sensitivity, durability, and energy efficiency in a single system remains extraordinarily difficult. Nature solved that engineering challenge millions of years ago. The result is the human hand. 27 bones, dozens of joints, more than 30 muscles, a complex network of tendons, thousands of sensory receptors, and a constant dialogue with the brain. A masterpiece of biomechanics, a masterpiece of neuroscience, and one of the most extraordinary structures ever produced by evolution. The next time you pick up a pencil, shake someone's hand, play an instrument, or simply touch the world around you, remember what is happening beneath the skin. Because inside your hand exists one of the greatest engineering achievements in the history of life. And it has been with you all along.